Hello, everyone. Welcome to part two of our lecture on chaos theory, where we will further explore the mathematical logical implications of chaos in the realm of proeminently economics, um, Paris, advertisement, marketing, um, capital gain, capital accretion, and further financial reinvestments, vested interests as such, and the totality of the ever functioning flux of socioeconomic capital, as well as materially contingent capital. And so here's the feedback, which is found from all the application of chaos theory onto the entire or onto a mappable field of materialistically instantiated economic reality. Here's the feedback. Feedback, like non-linearity, is also common in real-life events. Feedback is a characteristic of any system in which the output or result affects the input of the system, thus altering its operation. Feedback is most commonly observed when a microphone is in use. Some of the output signal is literally fed back into the system and causes the screeching sounds that engineers and musicians dread. Feedback can, however, be useful in the production of amplifiers where it is deliberately looped back into a system. Feedback is also observed on the trading floor and is actually a form of self-regulation. For example, if prices rise too high, demand falls, causing the price to drop. The original arrangement feeds back into the system and the prices readjusts. We can also see feedback loops when an enzyme produces a copy of itself in a chemical reaction. This is a positive feedback loop. This happens when DNA becomes a living organism and is very common in organic chemistry. So as we can see how our body interprets the feedback loop as a way of interpreting precisely the living organism which we are representing in the form of linguistic descriptivity. And lecturing, right? Since I am filing these under lectures, since I am not discussing with anyone, but since I have the entire apparatus of communication necessary to entertain dialogues at a maintained level of interest and communication, then we can assume that this channel might in fact appear dialogical or trilogical, or in fact chorological in the sense of chorus. Chorological, right? An invented word which allows me to talk about a chorus of people talking together, not necessarily at the same time, but ultimately all achieving a noetic field of comprehension which will be incomparable at the scale of humanity and at the scale of planetary endeavor. Some naysayers would tell me that this is an unachievable goal, but I would tell them that if it is in fact unachievable, then show me how much you care to prove your assertion. And so, However, scientists have tended to ignore feedback to create simple models that are easier to study and work with. They knew about feedback and complexities but did not understand them. For example, it is much easier to study population as a simple linear system than one involving feedback and complexity. A simple linear equation for population growth x is x underscore next equals rx, where r is the rate of growth of a population. It is easier to solve. Even though scientists knew that this year's population feeds into the next year's, that population growth is a feedback loop. They preferred to keep the model simple so that it would be manageable. Oscillating systems become chaotic because they possess an element of feedback. Chaotic behavior results when nonlinear forces are turned back on themselves. This is called nonlinear feedback and is an essential prerequisite for chaos. Let's now have an example of nonlinear feedback. The three-body problem. An example of a simple linear system that exhibits nonlinear feedback effect is the classic three-body problem of gravitation. Consider a moon orbiting a planet. The path that the moon takes is well known. It was fully described by Sir Isaac Newton's 1642 to 1727. Mathematical laws of gravity. But suppose we introduce a second moon of the same size as the first. Would the moon's orbit now be only slightly more difficult to calculate? It turns out that the simple deterministic equations which govern the three-body problem system are unsolvable. They cannot predict the long-term path of the orbiting moon. Aha! Okay, so further problem arise for the empirical and objective observation of a physical phenomenon of material and concrete property. The reason why the three-body problem cannot be solved is that gravity is a nonlinear force. Specifically, it is inverse square. In a three-body system, each body exerts its force on the two other. This produces nonlinear feedback and results in chaotic motion of the moon's orbits. But we have now solved the three-body problem by demonstrating that the orbits are inherently unpredictable. Such a solution would have been considered nothing short of sacrilege a few years ago. An amateur biblical scholar, Immanuel Velikovsky, 1895 to 1979, was dismissed by astronomers as a complete crank when he argued in his World in Collision, 1948, that the orbits of Mars and Venus had changed drastically around 1000 before Christ. His theory did help to resolve some difficulties with the chronology of the ancient world. Only gradually did we realize that our solutions to the equations of the planet's motions were approximate, and we could not define the range of possible inaccuracy. Now, with chaos theory, scientists can escape from ignorance of their ignorance. Chaos modeling. During the past 2 decades, scientists working in fields as disparate as weather forecasting, fluid mechanics, chemistry, and population biology have been developing models for natural phenomena that takes non-linearity and feedback into account. These models display 2 incongruous features. First, they consist of only a few simple equations. And second, solutions to these equations are complex and sometimes unpredictable. The analysis of these models and similar behavior in experiments is what we now know as chaos theory. Right? So, theorization implies modelization. If we take the simple equation x squared plus c equals result, where x is a complex number that changes and c is a fixed complex number, and continuously feed back the result into the changing number x slot. That is, we iterate the equation. Chaotic pattern like these are produced. Okay? This is an iteration of a simple function using complex numbers. This is a fractalized pattern, right? Applied onto a map, right? Creating a form of potentially what they would associate here with the formation of a snowflake, right? So the reaction of water coming down from the atmosphere might be a fractal, creates a fractal structure within the water, right? It might be dependent on the exact way the snowflake falls, but the inherent beauty of the structure of the universe is shown through in the downward pattern through which the snowflake falls. Questions of long-term behavior. Chaos theory works by asking questions about the long-term behavior of a system. Instead of making predictions about the future state of a system, chaos attempts a qualitative study of the system by concentrating on behavior that is unstable and aperiodic. Conventional astronomy, for example, is interested in knowing when a system of 3 planets will line up. In contrast, chaos theory asks, what circumstances would lead to elliptical orbits or circular ones? What characteristics will all solutions of this system exhibit? How does this system change from exhibiting one form of behavior to another? The signature of chaos. A distinguishing feature of systems studied by chaos theory is that unstable aperiodic behavior can be found in mathematically simple systems. Very simple, rigorously defined mathematical models can display behavior that is awesomely complex. Another distinguishing characteristic of chaotic systems is their sensitive dependence on initial conditions. Infinitesimally small changes at the start lead to bigger changes later. This behavior is described as the signature of chaos. This feature of chaotic systems is seen by some scientists as an important source of novelty and diversity in our natural world. Other scientists see this as a boundary where human knowledge runs up against limitations, where nature decrees, here you can go no further. And so the presupposition is that chaos brings us back to naturality. Right? And I would say that against order might be applicable to naturality as well. And as we see, the natural order is in fact a palpable phenomenon, as such as is maybe other forms of order. But I think the arrestation of the process is an illusion in the process of us understanding chaos. Right? The here we can go no further is a defeatist statement, allowing us maybe a small respite towards understanding the final goal of chaos theory as it is applied or understood or potentially even rejected. The literal devil. To explain sensitive dependence, mathematical physicist David Ruel tells this story. The little devil, presumably having nothing else to do, decides one day to upset your life. The devil does this by altering the motion of a single electron in the atmosphere. But you don't notice. Not yet. After a minute, the structure of turbulence in the air has changed. You still don't notice that anything is amiss. But after a couple of weeks, the change has taken on much larger proportions. And while you are having a picnic lunch with someone rather important, the sky opens and a hailstorm begins. Now you notice what the little devil has achieved. Actually, she wanted to kill you in a plane crash, but I talked her out of it. Let's now look at a history of chaos theory and meet the people who helped shape it. Benoit Mandelbrot and fractal geometry. Benoit Mandelbrot, 1924, a Polish-born French mathematical physicist who worked for IBM, developed the field of fractal geometry, which played a key role in the emergence of chaos theory. He did most of his pioneering work in the 1970s and published his findings in an illustrated and erudite book called Fractals, Forms, Chance, and Dimensions. No one understood what he was on about, largely because the prose was difficult to fathom. In 1977, a much refined version of that book was republished as The Fractal Geometry of Nature, and fractal geometry caught the imagination of scientists. Chaos and order in economics. Mandelbrot, a mathematical jack of all trades, started his work in economics. Economics believed that small transient changes has nothing in common with large long-term changes. Mandelbrot investigated this, but did not separate small changes from large ones. He looked at the system as a whole. I put the price data over several years for cotton into the computers. I noticed that while each particular price change was random and unpredictable, the sequence of changes itself was independent of scale. Indeed, curves for daily and monthly price changes were perfectly matched. The degree of variation had remained constant over 60 years, spanning 2 world wars and a depression. In other words, within the chaos, there was order. Chaos on the telephone lines. Mandelbrot also worked on telephone lines used to transmit information from computer to computer. Engineers were puzzled by the problem of noise in the lines. The current carries the information in discrete packets in the lines, but some spontaneous noise could not be eliminated. Sometimes it would wipe out the signal, creating an error. The interference was random, yet it occurred in clusters. I started to investigate by working with time, dividing the day into 2, then dividing that period into 2, and so on. He found an hour with no errors, but when he divided the hour with errors into 2, he found again a period with no errors and a period with 2 errors. Again, when he divided the period with errors into 2, the same thing happened. One period error-free, and one period with errors. There was always some time with no errors. And there was a consistent geometric relationship between the bursts of errors and the space of clean transmission. This phenomenon was incomprehensible to engineers, but mathematicians knew this as the Cantor set, a pattern that is created by removing segments of a line, then removing segments of the segments to infinity, leaving a dust of points arranged in clusters. Instead of increasing signal strength to drown out the interference, the engineers were advised to arrange a more modest signal and to accept that errors would happen. They had to arrange a way to catch and modify them. Measuring the coast. In a well-known paper, Mandelbrot asked, "How long is the coast of Britain? Suppose we measure the British coastline with a meter stick. The answer will be approximate, as the little nooks and crannies will be overlooked by this particular measure. But say we measure the coastline with a smaller scale, say 10 centimeters, and repeat the process. Here, a great length will be arrived at because the measure can go into those smaller spaces and count them. If we set the divider at 5 centimeters, the measurement will be bigger. So if we measure the coastline with smaller and smaller scale, the answer will become larger and larger. As we approach towards a very small scale of measurement, the coastline becomes longer and longer without a limit. Fractal dimensionality is what comes out of this conscientization. Mandelbrot suggested that what we observe depends on where we are positioned and how we measure it. Consider a football. From far away, it looks like a two-dimensional disc, but when we get closer, it becomes a three-dimensional object. So what about the areas in between the points far and close? At what point does a two-dimensional object transform into a three-dimensional one? Mandelbrot described systems with fractional dimensionality with the terms fractal. The coastline of Britain is an example of fractals, and he argued the only way to solve this problem is to move from ordinary three dimensions into what he called fractal dimensions. What are fractal? The geometry that we are all used to is attributed to Euclid, a Greek mathematician circa 300 before Christ. Euclidean shapes are regular: triangles, squares, circles, rectangles. Fractal geometry is the geometry of special types of irregular shapes. Fractals are a way of measuring the qualities that are otherwise have no clear definition. The degree of roughness or brokenness of irregularity in an object. And so, what is inaccessible? Indeed, a fractal is a way of seeing infinity. Mandelbrot, I coined the word fractal in 1975 from the Latin fractus, which describes a broken stone, broken up and irregular. Fractals are geometrical shapes that, contrary to those of Euclid, are not regular at all. First, they are irregular all over. Secondly, they have the same degree of irregularity on all scales. A fractal object looks the same when examined from far away or nearby. It is self-similar. Self-similarity implies that a subsystem of a fractal system is equivalent to the whole system in the fractal triangle. Each small triangle is structurally identical to the large one. Some fractals, though, are not only statistically self-similar. Their magnified small pieces do not superimpose on the entire system, but they do have the same general type of appearance. Fractals can expose the abstract geometrical nature of chaos, particularly in the form of computer graphics. Within the overall shape, there lies a repetitive pattern whose exquisite substructure characterizes the nature of chaos, indicating when predictability breaks down. Fractals are everywhere. Fractals also provide us with an immediate link with nature. Trees and mountains are examples of fractals. They are everywhere. Returning us to the Pollock-like patterns of movement from afar. Come over and see my fractals sometimes. The Julia set. Fractals can lead to beautiful graphics, and some fractals have been known for years. Gaston Julia and Pierre Fatou, during the First World War, discovered the Julia set. It explores imaginary numbers in a complex plane. Imaginary numbers are produced when we look for the square root of a negative number. The square root of -1 is considered to be I, and the square root of -4 is considered to be 2i, I being the imaginary dimension. But at the same time, nobody realized the significance of these sets for physics in the world. But they did have sets of patterns when these numbers were plotted. beautiful patterns that had no singular type. The use of fractals. Nowadays, fractal geometry is used to describe many complex phenomena. Fractals help us understand turbulence, not just how it arises, but the motion of the turbulence itself. Blood vessels can also be considered as fractals, as they can be divided down into smaller and smaller sections. They perform what has been described as dimensional magic, squeezing a large surface area into a limited volume. The lungs or digestive systems are also fractal. So are earthquakes. The distribution of earthquakes was known to fit a mathematical pattern. This pattern was picked up by geologists and found to be fractal. The fractal dimensions of a metal surface also tells us a lot about its strength. Mandelbrot has also lent his name to this famous fractal. It is known as what else? The Mandelbrot set. Millions of people around the world watched fractal mathematics without knowing it when they sat through the Star Wars film trilogy. Images of alien landscapes in the films were generated on computer using fractals. Indeed, fractals are now an important part of special effects in film. Edward Lorenz, 1917. A meteorologist, was the first to record a known instance of chaotic behavior. Lorenz started his postdoctoral work in 1948 at the Department of Meteorology, Massachusetts Institute of Technology, MIT. In 1955, he became the director of a project in statistical weather forecasting, a field that was pioneered by his department. Edward Lorenz. The first mathematically generated chaos that I encountered was produced by using a primitive model of a global weather system. The model would give a rough idea of how real weather behaved. It contained 12 variables. Following the example of astronomers in the 18th and 19th centuries, Lorenz used hand computation to estimate the solutions. Later, using computer models of the Earth's atmosphere and oceans, Lorenz studied the interrelationship between three nonlinear meteorological factors: temperature, pressure, and wind speed. I found that very small changes in the initial conditions produced widely varying and unpredictable responses. How could a simple three-equation model give us such a bizarre result? Lorenz was forced to conclude that this type of response was inherent in his model. In 1963, he published his results in a paper entitled Deterministic Non-Periodic Flow in the Journal of the Atmospheric Sciences. It took almost a decade for researchers to grasp the significance of this paper. Small differences, big consequences. Lorenz's discovery of the phenomena of chaos is often related to an interesting story. One day in 1961, the story goes, Lorenz decided to take a shortcut with his weather machine. He wanted to examine one sequence at greater length. So instead of starting the whole computer run from the beginning, he started halfway through. He taped in the numbers straight from an earlier printout and went away to get a coffee. When he came back, he could hardly believe his eyes. The newly generated weather was now near the original. They were two completely different systems. Then he realized what had happened. He had tapped in the number 0.506, the number stored on the printout, whereas the original number from the computer's memory was 0.506127. The small difference, 1 part in 5,000, was not inconsequential. Lorenz realized that minute differences in the initial conditions, like a puff of wind, could prove catastrophic. The consequences of his discovery were spelled out by Lorenz in these words. It implies that two states differing by imperceptible amounts may eventually evolve into two considerably different states. If then there is any error, whatever, in observing the present state, and in any real system such errors seem inevitable, an acceptable prediction of the instantaneous state in the distant future may well be impossible. The water wheel example. One example used by Lorentz to demonstrate chaos is the water wheel. This simple mechanical device is capable of astonishingly complicated behavior. At certain slow speeds, the system works fine, but when the water flows is increased, the wheel turns faster, the buckets have little time to fill up or become empty, and the behavior of the system becomes chaotic. The spin will then slow down or even reverse. It never repeats itself in any predictable patterns under these conditions. When the chaotic behavior of the water wheel is plotted, it produces a very beautiful graph, a double spiral in space that is known as a strange attractor. Strange attractors, complex systems in general, exhibit a property that mathematicians call attractors. Attractors represent the states to which the system eventually settles depending on the properties of the system. Imagine a marble swirling around a bowl. The marble eventually settles at the bottom of the bowl. The point at which the marbles settle attracts the marble. Another way of thinking about attractors is to look at some real-world situations where certain conceivable modes of behavior just do not occur. A pendulum in a clock in good working order does not swing gently at times and violently at others. Arctic temperatures do not occur at the equator. Pigs do not formally fly. Unusual things that do occur thus belong to a special area, or to put it technically, a restricted set. This is the set of attractors. And so on that note, let us end it there, and let's do our third lecture soon enough, and it will be on the cultural and identity attractors, right, versus the chaotic attractors, and the sense of potentially the symbolization and further subjectivization of attractors in their strange and charming ways.